All right, hello AP students, and welcome to your very short walkthrough on the initial understanding of rate of reaction, specifically average rate of reaction and factors that affect it for a chemical reaction. We aren't going to actually have an AP problem for this walkthrough because the information that we are given is really background leading us up into the AP tested topic. But I am going to walk you through a couple conceptual just to make sure everyone's on the same page, particularly in how we can use average rate of reaction as a predictor in stoichiometry for the amount of product produced or reactant used up. So question number 4, there is a container of 10 milliliters of 2 molar of X and 30 milliliters of 1 molar of Y. Okay. How would the rate of reaction be affected if the solution is heated up to 500 Kelvin? So the big thing here is we're considering our factors of collision essentially, right? So we know that there's kind of two main ways that you can look at affecting the rate of reaction. You can look at affecting the rate of reaction via collision and increasing collision, or you can look at it via the activation energy and changing the pathway. So when we think about temperature, temperature is dealing with this kind of approach to increasing our rate of reaction. So what we would say if we heated up the container to 500 Kelvin, we would see that the reaction rate would increase. Okay. As the collision frequency and percent of particles that can achieve the activation energy increases. All right. B, how would the rate of reaction be affected if the concentration of X is increased to 2.5 molar and the concentration of Y is increased to 2.0 molar? So again, what we would see here is concentration in this term is really just talking about general amount. Like we just have more particles in the same container. Okay. And so what we would see here again is we are addressing part 1, increasing of collision, and we say that the reaction rate would increase. And I'm actually just going to kind of copy and paste this answer and modify. Copy. The reaction rate would increase as the collision frequency would increase due to more particles, okay, being present. All right. So that's kind of that. It was really nice. Like I said, today's topic was kind of a warm-up. And so let's go ahead and go to question number 5. This asks us to consider, now that we know how to create a relationship between rate of production or consumption, how can we use it in stoichiometry or stoichiometric processes, calculations? So given the decomposition of a reaction, C12H22O11 solid goes to 11 waters and 12 carbon solid. And the rate of decomposition of sucrose, our original reactant compound, is 0.825 moles per minute. How many grams of carbon could be produced in 43 seconds? So the big thing here is that you have to keep in mind is that what we're given is we're told that we have 43 seconds. Okay, we're told that this is our time limit, 43 seconds. Now, our rate is given in minutes. So let's convert 43 seconds to minutes. So there's 1 minute in every 60 seconds. Okay, now we are in minutes. Okay, some amount of minutes. And we say, well, I know that in a minute, I am going to decompose 0.825 moles per minute, which means, by the way, that rate-wise, I am going to produce at a rate of 0.825 moles per minute, right? So being decomposed can be flipped, okay, to produced. So I know I'm going to produce at a rate of 0.825 moles per minute, all right, of carbon. But remember, what we got to notice is there's a stoichiometric relationship between carbon and our sucrose, which is being decomposed at a given rate. So to adjust my rate of production of carbon, I need to acknowledge the stoichiometric relationship between the production of carbon and the consumption or decomposition of sucrose, C12H22O11. And that modifies my rate to be stoichiometrically appropriate to the carbon. And then I say, well, I'm in so far moles of carbon. I'm in moles of carbon, and I realize something. I should move this and write sucrose just to help clarify. C12H22O11, and that way you can see that I canceled out everything. Okay, and so now I'm left in moles of carbon, but I want to be in grams of carbon. So now I'm just going to do by my molar mass. So I'm going to say for every 12.01 grams of carbon, I have 1 mole of carbon. So I'm going to find again that my moles cancel out, and I'm just left in grams of carbon, which is exactly what I wanted to be in. And I would see that I would have approximately to the sig fig is about 3. I think my calculation on my workbook only reported to 2. So I personally don't have easy access to a calculator right now, ironically. So I'm going to say it's going to be about 85 point something. I'm sure it's going to be, should be to 3 sig figs, 85 grams of carbon. And I'm just making a note that this should be to 3 sig figs. Okay, so that's how we can use rate of reaction in a stoichiometric process for predicting both production and use of a reactant. So really good work, you guys. Tomorrow we will get into rate law and eventually integrated rate law. And this is, by the way, a pretty AP problem heavy workbook. You will see that you have a significant amount of long FRQs regarding rate law and integrated rate law, which are our upcoming topics. So if I were you, please start planning ahead for completing these workbook problems in preparation for your unit 4/5 AP exam, where if you would like the curve, you are going to have to complete both unit 4 AP problems and the substantial amount of unit 5 AP problems. All right, guys, good luck. See ya.